to the next session of Fundamentals of Process Engineering. So here we'll be discussing regarding the week 6 syllabus problems. So we'll move on to the first question. Statement 1. In sensible heating process, the humidity of air is constant, but the dry bulb temperature increases. And statement 2. In a sensible heating process, relative humidity increases. So we'll discuss each term one by one. So what do you think is a sensible heating process? So in sensible heating process, you only increase the temperature of a product, you do not induce phase change. So increasing a temperature, let's say of water from 30 to 100 degrees will be sensible heating. But the moment the water starts evaporating and that is boiling and evaporating, it will no longer be sensible heating. So only when there is no phase change and an increasing temperature, you call it sensible heating process. So what is the term humidity? How do you define humidity here? So humidity is the amount of water vapor divided by the total amount of air present. So that will tell you the amount of water vapor that is present in the air and is termed as humidity. And dry bulb temperature here means that when you measure the temperature of any fluid or any product, say by using a thermometer, whatever temperature it shows is called dry bulb temperature. That is the normal temperature that is measured using the thermometer is called dry bulb temperature. So in a sensible heating process, the humidity of air is constant but the dry bulb temperature increases. Any clue whether this is true or false? So we'll discuss the answer. The humidity is the amount of water vapor in air divided by the total amount of air. But this differs from relative humidity mentioned in the second statement. So relative humidity is the amount of water vapor in air compared to the total amount of water vapor that can possibly exist in that particular temperature. So if you say that your air has certain amount of water vapor, that need not be the maximum that is possible at that temperature. So the relative humidity will actually compare the amount of water vapor that you have in air currently to the total amount of water vapor that can possibly exist in that particular temperature. So that is relative humidity. So when you look at a humidity chart, when you mean sensible heating, I said you are increasing the temperature. Let's say you're going from point A to point B here. So when you go from point A to point B, here the x-axis or the bottom scale represents your dry bulb temperature. Here your right hand side y-axis represents your absolute humidity or the humidity that we are mentioning here. And each of these slanting lines, these represent constant enthalpy. So your air will have a certain amount of enthalpy present. So each of these slanting lines represent a particular enthalpy value, and each of these curved lines represent the relative humidity, the ones that you see here. So these represent the relative humidity. So if you go from A to B, you can see that your humidity remains the constant. Only the dry bulb temperature increases. So your statement 1 is true. But if you go from A to B, you can see the curved line. I mean, you're going from one curved line to another curved line here. So what starts from 100% here in A is going all the way till somewhere around 20%. So these curved lines actually represent the relative humidity. So when in sensible heating, although your humidity remains constant, your relative humidity actually decreases. It's always 100% here, and it is somewhere around 10% at this region of the chart. So as you go from A to B, that is you are increasing your temperature, your relative humidity decreases. So statement 2 is false. So the correct answer to this question is option A. Any doubts in this? If you want me to repeat the humidity chart, I can explain again. Or else we'll move forward. Moving on to question 2. Statement 1. The wet bulb temperature is defined as the temperature measured by a thermometer whose bulb is covered with a wet cloth. And statement 2. The dew point temperature is the lowest temperature attained when a maximum of air and water vapor is sensibly cooled. So, what about statement 1 and statement 2? So, what is wet bulb temperature here? So, wet bulb temperature, so if you may, as I mentioned in the previous slide, if you just measure the temperature of a substance directly by a thermometer, it is called as the dry bulb temperature. You can mention it as DBT. But if you cover the wick of the thermometer with a wet cloth or something, because of evaporation from the wet cloth to the air, this evaporation will lead to a certain amount of cooling in the near the thermometer. So this cooling will result in a reduction of the temperature. So as the water evaporates from the wet cloth, a cooling effect will be encountered, and because of this cooling effect, you will see a decrease in the temperature. Just a minute. So hence, wet bulb temperature is actually defined as the temperature measured by a thermometer whose bulb is covered with a wet cloth. So wet bulb temperature will tell you what is the maximum, what is the lowest temperature that can be achieved by evaporation of a fluid. So what is the lowest temperature a fluid can achieve after evaporation is done. So this is wet bulb temperature. A dew point temperature is the lowest temperature below which the water vapor in your air will start condensing and forming liquid. So dew point temperature is the lowest temperature where you can attain a mixture of air and water vapor. Below that, automatically all your water vapor will start condensing and forming liquid. So your statement 2 is also true. In the humidity chart, let's say this is your dry bulb temperature. Somewhere around 47 degrees is your dry bulb temperature. So how to calculate wet bulb temperature is that you go parallel to the enthalpy constant enthalpy lines that are present here. The slanting lines represent the constant enthalpy lines. So if you go parallel to the constant enthalpy lines all the way up to 100% RH. So this curve will represent 100% RH or 100% relative humidity. So you'll make a line parallel to the constant enthalpy line all the way till 100% RH, and when you drop down, this will be your wet bulb temperature. But for dew point temperature, you will just draw a line parallel to your x-axis all the way to 100% RH, and then you will drop down. So this will have your dew point temperature. So as you can see here, your dry bulb temperature will always be higher than your wet bulb temperature, and this wet bulb temperature will be higher than that of your dew point temperature. So the answer to this question is option C. Any doubt so far? Okay, moving on to the next question. Which of the following dryer is used for production of instant coffee and coffee powder? A. Spray dryer, B. Fluidized bed, C. Rotary dryer, or D. Tunnel dryer? Any clue which is the answer? You can post your answers in the chat as well. So for something like dairy products or any of these coffee powder, milk powder and everything, we use something called as a spray dryer. No, the answer is actually spray dryer. I'll explain you how. So you will have a liquid feed, that is your coffee slurry, for which you need to make a product. You need to make particles like powder form you need. So you will have a liquid feed or your coffee slurry here that will go on to an atomizer. This atomizer will spray these particles into very small. Will spray all these slurry in a very small particles, And these particles will pass through the drying chamber, where you will also send your hot drying gas as well. So because of these small particles, your surface area increases drastically. Because of high surface area and the presence of a hot drying gas, all these particles will immediately dry, and you will get all your particles collected here. Whereas the exhaust drying gas will go through a separate outlet. So any dairy products majorly, like say milk powder, coffee powder, spray dryer is what is used. In case of a fluidized bed, you will have beads or you will send all your slurry through the bottom of the tube, so that it will become a fluid, and you will have particles inside the fluidized bed as well. And in the fluidized bed, you will send your drying gas, and you will ensure that the product is dry. Whereas in case for rotary dryer that you said, you will have a long cylinder-like instrument, and it will be pretty slanted. So you will have a slanting dryer here, and you will send your feed through one direction, and it will correct through the other direction of the cylinder. And as it passes through the cylinder, you will also pass in the drying gas, and you will dry the system. Whereas in case of a tunnel dryer, there will be a very long tunnel, and then like a conveyor belt, where you will place all your products, and it will dry from one end to the other end. So generally all milk products and everything, you go for spray dryer because you want very fine particles for your final storage. So the answer to this question is option A. Moving on to question 4. In dash drying method, agents like glycerol monostearate, egg albumin and protein isolate are used. So any clue which is the drying method? So what is one thing that is common among all these agents, glycerol monostearate, egg albumin and protein isolate? Yeah, the answer is C. So the common among all these agents is that they tend to froth a lot. If you start whipping all these agents, they'll tend to froth a lot, and all these are very edible agents as well. So agents like egg albumin and protein isolate are frothing agents, and these are added to your food products, and they are whipped continuously to form a stable foam. And because of the stable foam, you will have an increased liquid gas interface, and this will increase the surface area and increase the rate of the drying as well. So here you can see in a picture, you will have a slurry like liquid like feed, and you will add all these glycerol monostearate or protein isolate that are edible frothing agents, and you create a froth. And then once you subject this to drying, you will have a very fine powder. So this is what is called foam mat drying. So the answer to this question is option C. Moving on to the next question. The moisture content at which the constant rate period ends and the falling rate period starts is called equilibrium moisture content, free moisture, intermediate moisture and critical moisture content. So any clue? Yeah, the answer is D. So if you look at the drying rate with respect to your free moisture that is present, so let's say we start from A. So at A, your product will have certain amount of moisture present. So when you start drying it, it will initially have a lag phase, and at one point of time, you will see a constant rate. That is, the rate of drying will be very constant. This is because the surface of your food particle will have your water vapor saturated on the surface. So if you give hot air, whatever water vapor is present on the surface will start evaporating continuously. And since you have a lot of water vapor at the initial stage, you will actually find that the rate is constant. It is entirely dependent upon your temperature and your outside pressure and the evaporation rate, and on nothing else. So at this stage, when you have an abundance of water vapor on the surface, you will have a constant rate. After a certain point called the critical moisture content, you will see something called as the falling rate period. This is because whatever was on the surface of the particle, that is whatever water vapor was on the surface of the particle, has now dried. So whatever is now inside the particle should come onto the surface, and then that should be evaporated. So for the moisture to come from the bulk of the particle to the surface, it has multiple other steps that needs to be followed, like diffusion and all. So when those become rate limiting, and when your surface moisture drastically reduces, at that time your rate will completely be controlled by the diffusion, that is the diffusion of the water vapor from the bulk to the surface. So those will become controlling instead of your evaporation rate. So at that point of time, when you don't have much moisture to evaporate, you will see that your drying rate starts decreasing. And in fact, for multiple products, it need not be just linear, it can also be a curve as such. It need not be linear. So the point at which your rate starts falling, that is you enter the falling rate period, is called as critical moisture content. So the answer to this question is option D. So this is also known as CMC. Any doubts so far? Okay, so moving on to the next question. So we'll move on to the numerical questions. A food product is dried in a pan of 0.2 meter into 0.24 meter into 0.02 meter using the air flowing at a velocity of 3 meter per second perpendicular to the drying surface. The temperature and the humidity of the incoming air is 40 degrees Celsius and 0.014 kg H2O per kg of dry air. The wet bulb temperature is 22 degrees Celsius. The humidity at the wet bulb temperature is 0.024 kg of H2O per kg of dry air. The latent heat at the wet bulb temperature is 2410 kJ per kg. What we need to calculate is the total rate of evaporation if the heat transfer is only due to convection. So what is given is that the dimensions of the pan are given. We are also given that the inlet air is flowing at a velocity of 3 meter per second perpendicular to the drying surface. So the direction in which the air is flowing is very important, because accordingly your equation for your heat transfer coefficient will change. So your final answer will also change depending upon the flow direction of your air velocity. So the temperature is given as 40 degrees Celsius. When converted into Kelvin, it comes out to be 321. And the humidity of the inlet air is given as 0.014. Your wet bulb temperature is given as 22 degrees Celsius, that is 295 Kelvin. And your latent heat is given as 2410 kJ per kg. So when you consider a rate as a constant drying period, this rate can be expressed in the form of RC is equal to H into T minus TW by lambda, where H stands for the heat transfer coefficient, T stands for the temperature of your incoming air, TW stands for your wet bulb temperature, and lambda stands for your latent heat of vaporization, and RC stands for your rate. So in this particular problem, all the values are given except for H. So we need to calculate the heat transfer coefficient in order to calculate the total rate of evaporation. So the equation that is given between heat transfer coefficient and mass velocity is known. In the lectures also, what we know is the expression between your heat transfer coefficient and your mass velocity. So I will shortly explain what is a mass velocity. So first, in order to calculate the mass velocity is nothing but your rho into your velocity. That is rho, the density of the air into velocity of the air is your mass velocity. So in order to calculate the mass velocity, you need to first calculate the density of the air. In order to calculate the density of the air, you need to know the specific volume. So we'll find out how to do that. The specific volume of a particular air can be given as 2.83 plus 4.56 into H, where H stands for the humidity of the air, into 10 power minus 3 into temperature in Kelvin. So we already know the humidity of the inlet air and we know the temperature of the inlet air as well. So with this, we can calculate the specific volume of the air. So if we substitute the values, E is equal to 2.83 plus 4.56 into 0.014, which is given in the question, into 10 power minus 3 into 321 Kelvin, which is your temperature of your inlet air. So when you substitute the values, you get your specific volume to be 0.9289. So from this specific specific volume, you can calculate the density of your air. So density of your air at that particular humidity, at that particular temperature can be given as rho air is equal to 1 plus h by v. So the derivation of these formulas are not explained in the lectures as well, and this is not in the scope of the course. So we'll just, as of now, we'll just directly substitute the values in the equation to calculate their rho of air. So h is 0.014 and the specific volume is what you calculated right now. So rho air is equal to 1 plus 0.014 divided by 0.9289, which gives you rho 1.0916 kg per meter cube as the density of air. So from this point onwards, we calculate the mass velocity. So as I told you, mass velocity is the density of your air into velocity of your air. So both of these are now available to us right now. So G is what is termed as your mass velocity. So G is equal to velocity of air into density of air, which is given as 3 meter per second into 1.0916 kg per meter cube. So when you calculate this, you get 3.2748 kg per meter square second. So the expressions that we have for the relation between your heat transfer coefficient and your mass velocity requires the input to be given in terms of per hour. So if you have your value in terms of per second, you need to convert it into per hour and then only substitute inside the expression. That will only give you the heat transfer coefficient. So when you convert per second into per hour, you need to multiply by 3600. So 3600 into 3.2748 will give you 11,789.28 kg per meter square hour. So this is your mass velocity in per hour unit. So only this you will substitute inside the expression for your heat transfer coefficient. So the expression for heat transfer coefficient with respect to your mass velocity varies for different kinds of flow. So for a perpendicular flow, H is equal to 1.17 into G per 0.37. So we know G right now and we can calculate the heat transfer coefficient from this expression, which is meant for a perpendicular flow. So H is equal to 1.17 into 11,789.28, that is your G per 0.37. This will give you 37.55 watt per meter square Kelvin. This is actually, the unit is wrong, so it's watt per meter square Kelvin. So this watt per meter square Kelvin, you need to convert it based on the units that is given in the options in the question. So that I'll explain shortly. So you have 37.55 watt per meter square Kelvin. So 37.55 will be your H. So to convert it into per hour basis, which we require for our final answer, we'll again multiply by 3600. So 3600 into T minus TW. So T is the temperature of your inlet air minus TW is the wet bulb temperature divided by your lambda. So lambda is given in kilojoules. So you need to convert it into joules. So 2410 into 1000 will be your latent heat of vaporization. So when you substitute these values inside the equation that we discussed in the previous slide, you will get the value of 1.4584 kg of H2O per meter square hour. So this, as you can see, this is not the unit that we require in the option. In the option it is given as kg H2O per hour. This is actually rate per meter square. This is actually kind of a flux that we are looking at. So in order to calculate the rate, we need to multiply this by the cross-sectional area. So you have a pan and your fluid is present on the pan. So the area of your evaporation is nothing but length into breadth. You will not consider the height in this case. So the cross-sectional area is length into breadth. So to calculate from the flux, you need to calculate the rate. You will calculate RC into cross-sectional area, which is 1.484 into 0.2 into 0.24, which comes out to be 0.07 kg of H2O per hour. So this will be the rate of your evaporation in this particular drying process. So the answer to this question is option D. Any doubts so far? Okay, so we'll move on to the next question. So calculate the total time required to dry a product from 35% to 12% moisture wet basis in an industrial dryer where 2.25 kg of the dry solid per meter square surface area is exposed to the hot air. The drying rate remains constant up to 16%. The equilibrium moisture content is 4% and the constant drying rate is 5 kg of H2O per meter square. We need to calculate the total time. So can anybody tell me what is equilibrium moisture content? So when you look at an drying rate graph, so this is where we're starting. Let's say we're starting from point B. So this will be your first 35% moisture and it remains constant up to 16%. That is your critical moisture content as we discussed few questions back. So this will be your critical moisture content. Xc will be your 16%. And then you see that your drying rate starts to decrease. So it says that your final moisture content that is required is 12%. So this will be your point D will be your 12%. So what is Xc in this case is that it is the lowest moisture content below which evaporation is not possible. So even if you keep it for a very long time, it will not go below Xc. So Xc will be your equilibrium moisture content with the ambient temperature, and at that particular temperature and that particular pressure you cannot evaporate the product more. So this is known as your equilibrium moisture content. So as you can see here, there are multiple phases involved. There's a constant rate here involved and a falling rate also involved. So since they have mentioned that from 35 to 16 there's a constant rate, so after 16 it obviously has to decrease and constitute a falling rate. So your total time will actually include your constant rate drying period as well as your falling rate drying period. So your total time for drying is time during constant drying period and time during falling period. So we have an equation for each and every period there whose derivation is mentioned in the lectures. So the time taken during a constant drying period can be given by Tc, which is the constant drying time, is equal to W by ARC. So W is the weight of the product and A is the area of evaporation. What is given here, we already know the weight of the product per meter square. So W by A is already given as 2.25 kg of dry solid per meter square. RC is your constant drying rate, which is 5 kg of H2O per meter square R. And X1 will be your moisture content at the starting phase and Xc will be your critical moisture content. So this is where you have a constant drying rate, which is why you have X1 minus Xc. And what is one thing that you need to make sure is that in this equation, whenever you're substituting moisture, it has to always be on a dry basis and not on a wet basis. So we have to convert wet basis moisture into dry basis moisture to apply in this equation. So this is for a constant drying period. So for a falling drying period, we assume that it is a linear dependence. So when you assume that it is a linear dependence, your falling rate will have W by ARC into Xc minus Xc. Xc is your critical moisture content, which is 16%. Xe is your equilibrium moisture content, below which no matter how much you evaporate, the moisture content will remain the same. And ln of X1 minus Xc divided by X2 minus Xc. So we already have Xe, Xe, X1 and X2 given in the question. We have all these variables as well. But the problem is that all of these are on a wet basis. So we need to convert it into dry basis. So to convert a moisture into dry basis, moisture of dry basis is equal to amount of water vapor divided by amount of dry solid. So here you will not have total solid, you will have only the amount of dry solid. So this is equal to moisture of in terms of wet basis divided by 1 minus moisture of wet basis. So if you consider 100% to be your total amount of your solid, let's say 35% is your moisture. So the 100 minus 35 will be your dry solid, which is why we are having 1 minus x here. So if you substitute the values here in this equation, for x1 it is 35% moisture. So it is 0.35 divided by 1 minus 0.35. So this will give you the dry basis of x1. 0.5385 is what you are getting for this particular value. So similarly, you will do for the rest of the moisture as well, for both for critical moisture content, equilibrium moisture content, as well as your X2. So for Xe, it is given as till 16% your drying rate is constant, which means below which it starts falling down. I mean the rate starts falling down. So 16% will be your Xe. Xe is equal to 0.16 divided by 1 minus 0.16, which gives you 0.905 kg H2O per kg of dry solid. So X2 again, if you calculate, you will have 0.12 divided by 1 minus 0.12, which gives you 0.1364 kg of H2O per kg of dry solid. And Xe will give you 0.04 divided by 1 minus 0.04, which is 0.0417 kg of H2O per kg of dry solid. So now you have all the moisture in terms of your dry basis. So all you have to do is substitute back in these two equations and then calculate the total time required for drying. So substituting in the equation for time, the total time is equal to time required for your constant drying rate and your time required for your falling drying rate. So you have this as your constant drying rate and this as your falling period time. When you substitute the values, W by A is given as 2.25 and RC is already given as 5 kg per H2O per meter square hour. When you substitute these values, X1 and Xc values, what you get is time is equal to 0.1868 hours, which is 11.21 minutes. So the answer to this question is option A. So any doubt in how to calculate your dry basis moisture or the time, total time required? So in this particular equation alone, you have to make sure that it is all on a dry basis. If in the question it is already given in dry basis, you can just directly substitute the values, or else you will have to convert it from wet to dry basis and then use the equation. So moving on to question 8. 150 kg of paddy is dried from 21% moisture wet basis to 13% moisture wet basis. So what is the weight of the paddy after drying? So this is a straightforward balance equation. Can anybody tell me how to proceed with this? You have a feed of 150 kg of paddy going in with 21% moisture and it is coming out with 13% moisture. So what will you balance in this? What remains constant? When you dry a product from a wet to a dry powder, what remains constant? A is not the answer, but what remains constant? We'll go step by step. So when you're considering a drying process, only water vapor is getting evaporated. Your solid substance remains constant. So whether the inlet or the outlet feed, you can actually consider your solid as to be constant. So 150 kg is going in and X1 is 0.21 wet basis. You need to find out what is P here. Let's say P is your product. You need to find out the total amount of P here and X2 is given as 0.13. So you already know that your solid balance, that is your dry solid, remains constant no matter how much water vapor is getting evaporated. So if let's say 0.21% of F is water vapor, then 1 minus 0.21 will be your dry solid. Is this clear? So 1 minus your moisture content will be your dry solid. Moisture content into F will be your water vapor. So if I say 0.21 of 150 kg is water vapor, then 1 minus 0.21 of 150 will be a dry solid. Same way for your product also. If 0.13% of the product is water vapor, 1 minus 0.13 will be your dry solid. So since dry solid does not change in your drying process, this will be your solid balance. F into 1 minus moisture content in the feed equal to P into 1 minus moisture content in the product stream. So when you substitute the values, you get P equal to 136.2 kgs. Is this clear? So the answer to this question is option C. So all you can do is you can do a solid balance of your dry weight, since you know that it is not going to change. Moving on to question 9. 2.5 kg of air stream at 30 degrees Celsius having a 0.012 kg per kg of dry air. So here it is in a dry basis. Is mixed with 1.5 kg of air stream at a temperature of 30 degrees Celsius and 85% relative humidity, and these both stream mix and enter the dryer. The mixture is then heated to 60 degrees Celsius sensibly. The saturation vapor pressure at 30 degrees Celsius and 60 degrees Celsius are 4.5 kilopascals and 20 kilopascals respectively. The total pressure of the system inside the dryer is 101.325 kilopascals. So we need to calculate the relative humidity of the resultant air, that is the product field. So what is given here is that you have two streams. So let's consider it as A and the other stream as B. So A is 2.5 kgs and B is 1.5 kg. We already know the moisture content of the first stream, that is 0.012, but the moisture content of B stream is not given. Instead, you have something called as relative humidity given. We need to find out the relative humidity of the resultant stream. So this also includes a very straightforward mass balance only, but first we need to find out what is the moisture content of the stream B. So any clue how to find out moisture content from a relative humidity? So do you remember what is relative humidity? RH is the amount of water vapor present in the air currently divided by the total amount of water vapor that can possibly be present at that particular temperature. So relative humidity can be given by this formula, PV, which is your vapor pressure divided by saturation pressure. So saturation pressure will give you the total amount of, is indicative of the total amount of water vapor that can possibly be present, and your vapor pressure will give you the total amount of water vapor that is currently present in the air that you are dealing with. So you already have the saturation pressure given at 30 degrees Celsius. So initially these two temperatures are going in at 30 degrees Celsius. So you have to calculate your X1 at 30 degrees, X2 at 30 degrees Celsius. So if you substitute the values of RH and your saturation pressure, what is the vapor pressure that you are getting? So if you substitute your relative humidity as 0.85 and your saturation pressure is at 30 degrees Celsius is already given as 4.5 kilopascals. So if you multiply this, you will get your vapor pressure, which is 3.825 kilopascals. So from vapor pressure, it is easier to derive your moisture, that is your humidity. So H can be given in terms of your vapor pressure as 0.622 into PV, which is your vapor pressure, divided by P minus PV, which is your total pressure minus your vapor pressure. The derivation of this is also given in one of the lectures and it's pretty straightforward. It comes from the ideal gas law. So now that you know PV and total pressure of the dryer is also given, you can calculate the humidity of that particular stream. So if you substitute the values, you get 0.622 into 3.825 divided by 101.325 is your total pressure of the system minus 3.825. So this will give you 0.0244 kg per kg of dry air. This will be your humidity of your second stream. So now that you have the humidity of the first stream as well as the second stream, how do you calculate the relative humidity of your third stream, your outlet stream? So we are not drying anything here, it's just a mixture procedure. So whatever is the total amount of water vapor that you are sending in will be equal to the total amount of water vapor that is coming out. So using mass balance, since it's just a mixing process, your A plus B will be equal to C. The total amount of A plus total amount of B will be equal to total amount of C. So you have 2.5 kg plus 1.5 kg. So since it's just a mixing process, you will get your C equal to 4 kgs. And the second mass balance equation that you can do is, since total amount of water vapor remains the same because it's just a mixing procedure that you are looking at. So water vapor in stream A plus water vapor in stream B is equal to water vapor in stream C. So A into H1 plus B into H2 will be equal to C into H3. So you know all the values here. So A is 2.5 kgs. H1 is already given in the question as 0.012 kg per kg of water per kg of dry air. B is given as 1.5 kg and H2 we just calculated from here. And we know total amount of C is 4 kgs. So from this you can calculate your H3, which is your humidity of your outlet stream. So H3 comes out to be 0.0166 kg of kg per dry air, kg of water per kg of dry air. So any doubt so far? Had there been a drying process, you cannot just simply add these. Since it's just a mixing process, you can just add the water vapor present in both the streams to equate it to your outlet water vapor. So what is asked in the question is relative humidity, and what we have is humidity. So we'll just backtrace the same formula to calculate your relative humidity. So with H3, you can actually calculate the the vapor pressure in the stream 3. And what is mentioned here is that after mixing at 30 degrees Celsius, the mixture is heated to 60 degrees Celsius sensibly. So as I mentioned in the first question, in sensible heating procedure, your humidity remains the same, only your relative humidity decreases. Since your humidity remains the same, irrespective of whether it was 30 degrees Celsius or 60 degrees Celsius, your H3 will be the same, which is 0.0166. So this is what happens in a sensible heating procedure. Your humidity remains the same. So to backtrace, you will calculate the vapor pressure at 60 degrees Celsius, which is 0.0166 equal to 0.622 divided by PV into PV divided by the total pressure, which is 101.325 minus PV. So from this you can calculate your total vapor pressure, which comes out to be 2.635. So any clues, any doubts so far? So why we consider humidity to be constant irrespective of the temperature is because it is sensible heating. So from PV3, it is easier to calculate your RH. So RH3 is equal to PV3 divided by PS here. So RH3, sorry, there's a small change here. So PV3 is equal to 2.635 divided by your saturation pressure in the previous given at 60 degrees Celsius. So that is coming out to be 20 kilopascals. So you will actually substitute 20 kilopascals there instead of 101.325. So PV3 will be 2.635 divided by 20, which will give you 0.137. So your RH will be 13.7%. So the answer to this question is option C. So any doubt on how to calculate your relative humidity from vapor pressure, and then from vapor pressure you will have to calculate humidity. So in case you guys want me to repeat anything, I can repeat again as well. Just post it in the group chat. Okay, so moving on to question 10. The food product of a 12 millimeter thickness slab is dried from 35% moisture, that is dry basis, to 14% moisture, also dry basis, by flowing a hot air on both sides of the slab. So what is the time required for drying if average diffusion coefficient moisture in a product is 10 into 10 power minus 6 meter square per hour and equilibrium moisture content is 4%. So the moment you have something called a diffusion coefficient moisture, you know that the rate is not constant anymore. So your rate is actually dependent upon your diffusion. So the moment you have something diffusion controlling your drying process, it becomes a falling rate period. So for a falling rate period where you know that your average diffusion coefficient is what is controlling your reaction, controlling your drying process, this is the equation that you will use. So your falling rate time period is equal to 4a square divided by pi square d ln of 8x1 square, 8x1 star by pi square x2 star. So what these variables mean that A is the slab, half the slab thickness. So we are using half the slab thickness because you have a slab and you have air on both the sides. So it needs to dry only half the slab from one side. The rest half of the slab will be dried from the other side. So we actually calculate the thickness A to be half your slab thickness, which is 0.006 meters. So A will be half your slab thickness, and this is half only when you have air on both the sides of the slab. Otherwise, you will not consider this as half the thickness. So 4 into A square, D will be your diffusion coefficient. And x1 star is actually x1 minus xc. Xc is your equilibrium moisture content, below which your moisture content cannot reduce further. And x2 star is x2 minus xc. So you have pretty much all the parameters that is required. A will be 0.006, which is half the slab thickness. X1 star and x2 star you can calculate since all of these are on a dry basis only. And D is also given. So when you substitute these values in the equation, you have x1 star is equal to 0.35, which is x1, minus xc is 0.04. This will give you 0.31. Similarly, x2 star is x2 minus xc. So x2 is 0.14 minus xc is 0.04. So this is equal to 0.01. So when you substitute back in the equation, you have 4 into 0.006 square, which is your half the slab thickness, divided by pi square into your diffusion coefficient, which is 10 power minus 5, into ln of 8 into x1 star divided by pi square into x2 star. So when you substitute these values and calculate, the TF that you are getting will be 1.34 hours. The answer to this question is option A. So any doubts so far, anything that needs to be repeated, any of the questions, any explanation?